Hi there and welcome back to another video here on the Polaris School of Quantum YouTube channel. Today we are looking at a company called Atom Computing, which is, as the name suggests, using atoms to do quantum computing. And if you want to know a little bit more about what this company is about, what are they doing different from the competitors, and also where are they actually based, then stay tuned for today's video as we are diving deeper into atom computing. And as always, make sure to get yourself something to drink to stay hydrated throughout this video, and let's get started. So here we are on the website and it says Atom Computing, Atomic Array Quantum Computing. Atom Computing builds highly scalable gate-based quantum computers with arrays of optical trapped neutral atoms, which will empower unprecedented breakthroughs. So important, a couple of things ahead here, right? So it is atoms, and within the atom branch it is neutral atoms. So what do we mean by neutral atoms? Well, technically every atom is electrically neutral. So you have protons that sit in the nucleus, you have the electrons that are, let's say, building the shell of the atom, and in a normal atom configuration you will have the same number of protons sitting in your nucleus as you have electrons in the spheres or in the shell of the atom, and that's why, from looking at it from the outside, the atom is neutral. Now, if you rip off one of these electrons, it becomes a charged particle, which we call an ion. So then you basically remove an electron, so you remove one negative charge particle or one negative charge quantum, and that's when you end up with a positively charged object, which we call an ion. And ions are also being used to build some types of quantum computers. The advantage of an ion is that due to its electrical charge, you can use electromagnetic fields to control and manipulate those building blocks. Now here we have neutral atoms, so basically like charge-wise neutral entities. So you have to use different types of techniques to actually manipulate and to put these atoms into specific positions so that they shape this array. This is done via optical methods. It also says here optically trapped neutral atoms. The technique is called optical tweezers. So like a tweezer that you usually take to grab a small object, you will then have optical tweezers, so using kind of laser beams, which are electromagnetic fields that are evolving over time to kind of trap these atoms in a specific position. And then the idea is that using this, you can actually build quantum computers with it, and then you can control those atoms, you can manipulate their states, and thereby render them as qubits and perform activities like build algorithms with this. And this is this idea of gate-based quantum computers, right? So you have qubits, you apply gates, similar to like a digital computing today, where you have your computer and you apply different logical gates that can then, based on the gate that you apply, perform specific operations, like NAND gates, AND gates, OR gates, and so on. So now let's move on. What do they have to tell us here? So 1200 plus fully connected qubits enter the logical qubit era with Atom's AC1000 system. And we will not look into this right now, but let's scroll a little bit further on. So announcing a game-changing collaboration, building quantum supercomputers with Microsoft. So there's a collaboration with Microsoft ongoing as well. Then we see quantum computing at scale. Applications with commercial value require universal gate-based quantum computers with large number of error-corrected qubits, long coherence times, optimized connectivity, and fast operations. Our technology is poised to exceed these critical requirements. Let's also quickly step out here. So universal gate-based, that says something about the type of gates that you can apply. So in classical computers, you have this specific set of gates that if you can actually build them, you can do universal operations with it. The same is true for quantum computers. You have specific gates that you need to be able to apply so that you can do arbitrary types of operations with the system. error-corrected qubits. So why is error correction a topic here? In classical computers, it's not. This has to do something with the ideas of superposition and entanglement, more or less. Because if one of your qubits is flipping, is having some issues, then you can basically spread this error across the whole system by the superposition, so that it becomes very difficult to actually track and correct for that. So error correction is a very complicated topic. There's a lot of research, active research ongoing on how to do a proper error correction without adding too much, let's say, load onto your system, because technically you will not be able to map one physical qubit on one logical, so error corrected qubit, but you need a couple of physical qubits to build one error corrected logical qubit. So there's a lot of research on that. Why are these qubits actually so prone to errors? That's because usually we encode the quantum information in energy levels. So think about, for example, your ion. You might excite an electron, or maybe also your atom. You might excite an electron into a higher electronic state. So if you're in a very simplistic and non-quantum way, think about the nucleus sitting in the center, and then you have the electron running around it. Now, if you kick this electron into a higher orbit, then it has more energy and it's in this higher state. And that's how you can encode more or less a qubit, right? Because now you have an electron in a lower state means 0, and in the upper state it means 1, for example. And then you need to figure out how to read out these things, of course. Now, these levels, they are quantum states, they are quantum levels. So by definition, they are the smallest energy levels that you can find, because that's what quantization is about. Quantization is always at the smallest limits. So everything that can kind of disturb the energy on your atom or on your ion or on your superconducting qubit, whatever you want, can actually influence the state of your qubit. So that's very critical, because that means if you, for example, put a little bit of heat into your system, heat is basically statistically distributed energy. You have some energy that comes in the system. If you have a particle from space that kind of shoots through your atom system, your atom array, and might hit one of these atoms, then it creates some energy level change, or might create some energy level change, and that's where you have these errors. So these errors, they are always happening at every single point in time. You want to make sure that the operations that you're performing, so the gates that you're performing, they have a low error themselves. So that is like, let's say, high, I don't know if you like what you want to call it, like a high performance, a very accurate performance of your gates. The other thing is this long coherence time. So if you put a qubit into a specific state, how long does it actually stay there? Optimized connectivity refers to how well can you connect your qubits, because if you think of the qubits sitting in an array, right, you have this two-dimensional array where they're sitting like in a matrix type of, or in an array type of architecture. Now, how do you connect this qubit up here in the upper corner with this qubit down here in the lower corner? So you need to have a very good connectivity. You need to create ways to kind of entangle them so that you can actually make use of this idea of entanglement and superposition in your system. And you also want to have a fast operation, because it doesn't help you to have a long coherence time. So it doesn't help you if you can build a system where like your excited state, your one qubit can be held for a minute, if it takes you 5 minutes to perform an operation, right? So you need to have fast operations and long coherence times, a good connectivity, error correction, and so on. So these are all the critical topics that a system architecture needs to fulfill. And that's also where today's quantum computers are competing against each other, so the different technologies. And everyone might have their advantage in one of these categories and might have a good reason why their technology has an advantage. And then over time, we will, of course, see which type of architecture works best, or maybe even best for a specific purpose, right? It could be that you have one that is extremely well connected, and therefore you have another one that has extremely low error rates. So with one you can build very, very deep algorithms, and with the other one you can build very, very wide algorithms or well connected algorithms. And then you kind of need to balance your algorithms between those. But that's, let's say, another discussion. Let's move on in the Atom Computing website. So there's a video which I'm not going to watch here. There is a call to action to explore careers. And then there's down here a news section. I'm recording this video in March 2026, and you can see that here this announcement, Atom Computing integrates NVIDIA NVQLink to accelerate scaling of its quantum computers, is from March 2026, so decently up to date. And then there's also explore our tech perspectives, learn more. The company is based in Berkeley, California in the US, as we can see down here. Now, let's quickly check out the technology part. So Atom's technology, our technology advantage, Atom Computing builds quantum computers using optically trapped neutral atoms to create arrays of nuclear spin qubits. We cool, trap, and control those qubits wirelessly using lasers. Our commercial platform, AC1000, harnesses the power of over 1,200 qubits to explore innovative quantum algorithms, pushing the boundaries of system performance and scale. And here in the background, we can see this optical equipment. So you see a couple of lenses, you see fibers and laser beams, and probably right here, I don't know, they might be adjusting the laser, the beam path, like changing and making it accurately to hit a specific position. I don't know. So now what else do we see here? We employ the nuclear spin of atoms, of neutral atoms, to construct qubits. Unique benefits of our technology include massive scalability, so neutral atoms held only microns apart with focused laser light lack electrical charge and can be tightly packed into an array. The atomic array can be expanded to thousands or millions of qubits without substantially changing the overall footprint of the system. So that refers to basically the size, right, of your quantum, in this case not chip, but of your atom cloud or atom array. Fidelity, neutral atoms are intrinsically identical, have been extensively characterized, and present no fundamental physics obstacles to achieving sufficiently high fidelity to enable fault tolerance at scale. So here, that is, let's say, relating a little bit to the solid state technologies, like for example superconducting qubits, where you artificially create a quantum system by using a superconductor and lithography techniques and printing this onto your chip. As a matter of fact, the quantum element itself is micrometers big, because you're basically using a superconductor which at these low temperatures behaves like a single quantum system, but it is micrometers in size. And with that, you have a huge area that is basically exposed to an environment. And this environment is a microscopic environment, right? Your wafer, the silicon wafer that it's printed on, is constructed of many, many, many atoms. And if you have a microstructure and you have atomic sizes, so nanometers or even less than nanometers of atoms that are placed below this, you are basically creating a system where there's like little disturbances that make every single one of these qubits a tiny little bit different from each other. And that's why you need this extensive calibration schemes. You are doing stuff to also make them differentiable from each other a little bit. And that of course makes it, on the one hand, it's a feature because you can differentiate them pretty well and you can control them separately. But on the other hand, it's also a disadvantage as it needs this calibration scheme, which you don't have if you use atoms, because atoms are always identical by nature. And this fidelity is then referring to, okay, if every single atom is identical, you exactly know what the energy levels are So how to get your qubit from 0 to 1. So you don't need to do any calibration or anything. You can just exactly control all of them exactly in the same way. And you can do that in a very controlled fashion because you don't need any broadband hardware. You just need something that exactly hits this transition. And that's why you can fine-tune everything extremely well. And that's why you can reach these very, let's say, precise controls of your system. Then you see here reduced complexity. So all of the control functions of neutral atom qubits are mediated by light propagating through free space rather than individual electrical cables attached to each qubit. So that's again related to the laser. And then long coherence. So the closer outer electron shell of alkaline earth metal atoms provides insensitivity to environmental perturbations, enabling our qubits to achieve industry-leading coherence times. And there's, of course, a scientific paper linked here with more information if you want to dive deep on that. Dive deep on that. Sorry. Now here you see the system, and that's maybe something that also catches your eye here. So comparing to other types of architecture, this system might seem a little bit bulky. So these are probably normal rack sizes, and you see there's not just one or two, there's many of those. And that, of course, has to do with all the optics equipment that you need to build these complex apparatus, right? So you need a lot of lasers, beam rays, like beam splitters, mirrors, and everything that you saw above in the setup, but times 1,000. So that's why you have this little bigger footprint. But on the other hand, we also see that there are people integrating this technology onto chip level already today. So this is also going to shrink in the future. This is just the first system, right? Built with equipment that used to be applied in a lab and now kind of finds its way into a productized shape. So what does the website say here? So AC1000, our universal gate-based platform, is commercially available for on-premise deployment. Leveraging our technology advantage, AC1000 offers better than threshold fidelities, 1200 plus physical qubits, all-to-all qubit connectivity, and advanced technical capabilities such as mid-circuit measurement with qubit reuse and reset and real-time conditional branching. Everything you need to build your own logical qubits. So there's also a lot of stuff in there. I'm not going to touch every single point of that, but interesting all-to-all connectivity. So you can connect every single qubit with every single other qubit. Advanced technical like mid-circuit measurement, so you can basically, you don't need to do the whole program execution and can only measure at the very end, but you can also have a measure sequence between your operations and then keep on going with your algorithm. And then also you see here this reuse, reset, and real-time conditional branching, where I guess there's some computer sitting in there that can make decisions upon the measurements that you perform. Probably related to this NVIDIA announcement we saw before. Then there's here a quote from the CEO and founder, Ben Bloom. Together with our partners, our team is building on decades of research in optical control of neutral atoms and quantum physics to empower scientific discovery, engineering advancement, and business innovations. We are excited to give quantum application developers a breakthrough computing platform to explore new possibilities. These decades of research, I mean, I'm not an expert on these neutral atom computers, but I think that also relates to the whole, let's say, characterization of atomic energy levels that has been done in the past. It relates to all the development that has been done on atomic clocks and all of that stuff that has been developed in the past, which is all kind of interrelated. Like every research that has been done on atoms and nucleus is kind of being used now, more or less, to build this type of systems here. So then we see collaborating in the quantum ecosystem. We are collaborating with software and application development partners worldwide to unlock the value of our large-scale quantum computing to bring their innovations to light. Our partner program provides developers an opportunity to secure early access to our systems, collaborate with our technical team, provide feedback, and explore valuable applications. So that's also interesting to see, right? So the focus of atom computing is to build the hardware, and then when it comes to the software and the application layer, they are out. So they're not building this. They are basically pulling in partners, and the partners then enable the software layer and the application layer. Again, we see some tech perspectives linked down here. And I encourage you to check those out if you are interested. There's also a white paper listed here, which I quickly want to go into because this is something that oftentimes we do not see with the companies, something that goes, let's say, into the technicalities. So I want to quickly browse with you through this to see to which level this goes down. So I think there's a bit of the explanation on the technology itself here. There's also something about the real-world applications, and I think this is very interesting. So here it really goes down into the, let's say, lower level techniques that are being employed, and I'm not going to go through all of this in today's video, but if you are interested in that, as always, let me know down in the comments below, then we can do a separate video about this. But here you can, for example, see it explains indeed this idea of the optical tweezers, nuclear spin qubits, fully integrated control systems, and so on and so forth. So everything that you kind of need in a, I guess, high enough level to easily understand that without going down into all of the equations, formula, and atom physics that you might want to know if you are doing actual research on that. On the products, we only see this one product for now, which is the ST1000. I think we've seen the main features already announced before. Let's see, what else do we have here? There's a couple of details mentioned down here. So AC1000 offers highly competitive fidelities, 1200 plus physical qubits, all-to-all qubit connectivity, and advanced technical capabilities such as mid-circuit measurement. I think we've seen these things before. With a total footprint of approximately 600 square feet or 56 square meters and moderate power requirements, the system can be integrated in existing office buildings. You see it is a neutral atom system based on yttrium-171 atoms. It's using the nuclear spin to encode the quantum information. 1200, well, I think, yeah, 1200 physical qubits with an all-to-all connectivity. You see the Q1 and Q2 gate fidelities are 99.9 and 99.6%. And there's also other information about the systems listed down here. On the software side, it says real-time conditional branching. We've seen that before. API access via OpenQASM and QIR. These are, let's say, the development environments. There's an emulator for 20 qubits available and additional integrations as well. Okay, then as always, there is a news and resources section. I'm not going to go through that. The tech perspectives, which we have seen before as well. These are articles that are, let's say, moving down deeper into the tech. There's a careers and a contact field as well. And as per usual, at the end of every video, I'm very happy that you are still here. Let's quickly also dive into the company describing itself in the About section. So, our singular focus, scalable quantum computers. Our team is developing large-scale quantum computers to help companies and researchers achieve unprecedented computational breakthroughs. Using arrays of optically trapped neutral atoms, we are building cutting-edge systems for on-premise deployment with advanced features such as long coherence times and mid-circuit measurement. Our unique approach to highly scalable quantum computing and path to fault tolerance offers new tools for quantum algorithm developers to tackle increasingly challenging applications. Then we have this beautiful view to the mountains here with, I guess, the buildings that the company is based in. We see the executive leadership team, which includes the founder and CEO Ben Bloom, which we've seen already before. There's also Jonathan King as co-founder and chief scientist, but we also see that other functions within the company are shown here. So you see there's VP Human Resources, Chief Product Officer, VP Finance. So you see VP Research Collaborations and VP Optical Engineering. So there are many functions of this company already represented. There's also a scientific advisory board, as it seems, and a board of directors linked here as well. Down here we see the investors, and I think that is maybe also interesting. We have seen that there are major collaborations before, right? So we've seen NVIDIA being listed, we've seen Microsoft being listed. And when I look through the investors, I mean, I'm not an expert. I see a couple of names that I've seen previously, but one which might be very interesting is that Lockheed Martin down here, which is also apparently invested into Atom Computing and probably also pretty well known as a player in the defense sector as well. But you also see Van Rock, Innovation Endeavors, Prelude Ventures, NSF, EIFO, Third Point, and Prime Movers Lab. Okay, with that, I think we are at the very end of today's video, of course. Atom Computing, a company that is using neutral atoms to build quantum computers, already has the first product out there and is basically working already in the software ecosystem and in collaborations on this, let's say, product and using this product. If you found this video interesting, make sure to subscribe to this channel so you don't miss out on the next one. I'm looking forward to see you for this next video. Until then, bye bye.